The US throws away 80 million tons of food every year, which averages out to 483 pounds per person in a year. That's a lot of food, and when it goes to landfills, it isn't just sitting there. It's releasing methane, a greenhouse gas 25 times stronger than carbon dioxide. On top of that, carbon dioxide levels are measured at 120 parts per million higher than they have been at any point within the last 800,000 years. We've already seen the impacts: stronger storms, rising sea levels, and ecosystems struggling to keep up. If we want to slow this down, we need energy solutions that don't rely on fossil fuels. That's where the microbial fuel cell comes in. The microbial fuel cell is an incredible tool. It's made up of about 4 different areas. We have our anode chamber over here, where our bacteria or organic matter is breaking down and releasing electrons. On the other side, we have our cathode chamber. And separating the two, we have our permeable exchange membrane. This allows protons to pass from the anode to the cathode chamber while keeping the electrons on the anode side. Within each container, we have our electrodes, a conductive material, and these can harness those electrons and actually create an electrical current, which produces the energy from organic matter. So before I dive into my product, I'm going to talk a little bit about the competition. There's a number of different renewable energy alternatives that we see within our everyday lives. Windmills are great for energy production, but can take up a lot of land mass and take a lot of resources. The same thing with solar panels. People who live in areas where you have these big solar panel farms going in are often unhappy about the issues that it caused with their everyday lives. We have composting, people using their organic waste in gardens or to help their soil fertilize, which is a great alternative but doesn't produce energy. The last thing we have is biofuel, where they're burning organic waste or organic matter. This is great to get rid of the waste and also produce energy, but can release a lot of byproducts into the air and isn't always the best alternative for energy production. So let's talk a little bit about the commercial feasibility of my product before I actually tell you what it is. So our consumers would be anyone in low income areas maybe who aren't able to fully pay their energy bills every week but need to be able to keep the lights on without paying those costs. Places in energy deserts who aren't always able to have electricity. Some places in Africa who aren't able to have energy all the time. The average consumer, this is very appealing to the average consumer because it lasts very long term. We have very little chance of product issues because they can just be 3D printed with little human work involved, and it helps solve real world issues. So our consumers actually feel like they're helping the world around them while getting the benefits for themselves. This averages out. The original sale price would be about $50 per unit because it costs me about $35 to produce the prototype. Now, if we start buying certain electrical components and 3D filament in bulk, this price could go way down, and the price of the actual unit would go down in turn. So let's go on to what the product actually is. So this is the MFC Leica lamp. On the left, I have some tests that I ran to test what compost samples were the best, what electrode materials, and how to actually get this to work. In the middle, we have the design that I made within Fusion 360 of the MFC Leica lamp, and on the right, we have the internal electrical components, which includes a battery storage backup system and a DC step-up converter that in turn goes to the light bulb socket. So here's some results of how it would work if people implemented these within their household. So per individual person, it'd save about 242 kilowatt hours in a year, $31, and reduce their CO2 impact by about 208 pounds. For the average U.S. family, it could be anywhere from 750 to 1,000 kilowatt hours, $100 to $130, and reduce their CO2 impact by anywhere from 650 to 850 pounds in a year. So the physical product, on the upper left, we have the 3D printed parts. In the middle, we have the assembly and how it fits together. And on the right, we have a picture of the actual physical product. On the bottom left, I have the materials used for the inner workings. And on the bottom right, we have the layout of the inner workings. So the concept of this design is it's just a normal lamp. It can switch on and off whenever you need it to. But the bottom unscrews, and the consumers are actually able to fill this lamp with organic waste, compost, leftovers from the day before of their choosing. And this can actually convert that organic matter into electricity. So it's very low maintenance, users are able to fill it up once and it'll produce energy for about 2 months without any sort of work on their part. And it'll just light up whenever they need it to. And it has a battery storage backup, so even after the 2 months ish is up, it's able to support for another week or so with that battery backup before they have to replace the organic matter within the product. So that's my application for the STEP competition this year. I hope you enjoy my product and see how much it could help the world around me. Thank you.